On the table here we have 5 spring balances, also known as Newton meters. They measure the force required to pull things along or lift things. We see this blue spring balance can measure a force of up to 2.5 newtons. Remember, capital N is the symbol for newtons, which is the unit we use to measure force. The green spring balance here measures up to 5 newtons. The brown up to 10 newtons of force. The red can measure up to 20 newtons of force, and the yellow to 50 newtons of force. So we can use these to lift things against gravity or to pull things along, and just see what sort of force is required to do that. Okay, so we're going to put these spring balances, or these force meters, or Newton meters I should say, put them to work and test a variety of things. I have a couple of little science helpers here. This is Ailish and Kian. Are you guys ready to do some science?
Yes.
Excellent. What are you going to do first?
Safety
goggles. Good job. All right, let's do some science, hey?
Yeah.
Okay, Ailish.
Yeah.
If you pick up the blue spring balance and hook the cord here, and we'll see what force is required to hold that up against gravity. Right, hold it up high so I can see. Hold it up straight. It needs to be held straight. Hold it by the top here, sweetie. Hold it here. Yep, hold it up nice and straight. Okay, so that's recording of a force of about 0.1 newtons of force required to hold this little loop of cord up against gravity. Alright, Kian,
Yeah.
do you want to lift up the car?
Yes.
Okay, let's see the force required to do that. Can you pick up the blue spring balance and hook it onto the front of the car? Good job.
Now do I lift it?
You do, yes. Lift it up all the way so the car's off the ground. Lift it up. Whoa, good job. Hold it there. Hold it there. Good. Hold it still. Hold it still. Good job. Now what we see is actually the spring balance has gone right to the bottom, past where the markings are, which means it takes more than the 2.5 newtons required to lift the car than this that this blue thing can measure. So, Kian, do you want to put it down? That spring balance doesn't go high enough, darling, so let's try the next one.
Next one.
Yeah, the green one. Because the green one can measure up to 10 newtons. Wait, is this our 10 newtons or is this 5 newtons? This is 5 newtons. Okay. Ailish, pass to Kian. Thank you. Hook that one on, Kian. You got it? Hook it onto the car. That's it. Now you need to lift it up straight again, just like you did with the blue one. Yep. Move away from the black tub, darling, so you don't have to hold it as high. There you go. That's better. Good job. Now, hold it still. Hold it super still. Can we just turn this green one here? Hold that. Do not move. Thank you. Let me just see on this. That. Hold it still. Hold it still. That is about 4.5 or so, or just a bit more. Maybe 4.6 newtons of force required to lift this car up against gravity. Okay, Ailish, let's measure the force needed to lift up this hula hoop, hey? We're going to start with the green one. So the green one measures up to 5 newtons of force. Hold it up. Yep, good job. Now we can see, hold it nice and straight. Hold this as straight as you can. Good job. We can see that it takes, what's that, is about 1.5 newtons of force, maybe slightly more than that, required to lift up the hula hoop. Now we could have actually, because it's using about 1.5, we could have used the blue spring balance, because that measures up to 2.5 newtons. But what was the issue, Ailish?
The hook didn't fit on this.
That's correct. The hook didn't fit. So we can still use the green one, can't we?
Yeah.
Yeah, good
But
job.
the yellow one would definitely fit. So,
Yes, the yellow one definitely does fit, but then it won't. Actually, put the yellow one on, we'll see. Because it measures up to, what was it, 50 newtons on this one, and we only need like 1.5 newtons to lift the hula hoop, we can see that the top hasn't, oh wait, that's the gram side, show me the force side. It, focus video, focus, there we go. It really hasn't moved down at all, has it, darling? No. So we have to actually choose a spring balance appropriate to the task, yeah?
Yep.
Yeah. Okay, Ken,
yeah.
ready to measure your scooter?
Yeah.
Alright, hook it on the handlebar. Now the hook won't go all the way around, but it will hook on enough to lift it up. Yeah, don't worry about trying to hook it all the way around, because it won't. Yeah, just there. Just lift the Newton meter up. Can you lift it up? Yeah, I know, it's pretty heavy, isn't it? Hey, you've got it airborne. Good job. The issue is, can't really see. That's why we need to hold it at the top. I'll just lift it up like this for you, okay? So that we can see.
Now,
No, don't hold it up, because that's kind of cheating, isn't it? We're just seeing what force is required to lift the scooter up. Focus fine. Okay, so it's about 16 newtons of force to lift this scooter up off the ground against gravity. I seem to have a dinosaur. Ken, what dinosaur are you right now?
blue.
Oh, you're blue. Which is what dinosaur? What sort of dinosaur?
The leader of the raptors.
The leader of the raptors. Yes, blue is the leader, isn't he?
Yeah, and I'm blue.
Yes, okay.
And all the raptors are girls.
Well, yes, that's right. They are all girls, aren't they?
And I'm
On that
a
movie.
girl.
Yes, you are. Are you a dinosaur? Or are you just a girl? But what's your favourite dinosaur?
Pterodactyls.
Pterodactylus. Good job. Ken, what's your favourite dinosaur? Quick.
Pteranodon and blue.
Pteranodon and which one?
Blue.
And blue.
Yeah.
Okay, so Velociraptor. Ailish,
Yeah.
come back please. This is a little bit sidetracked from physics, but come here. Teach my Year 7 students, because you said your favourite dinosaur is a which one?
Pterodactylus.
Pterodactylus. But what do most people call it?
Pterodactyl.
That's right, a pterodactyl, but you know better, don't you?
Yeah.
Yeah. Okay, Year 7s, I know everyone says pterodactyl. That was never a thing. It was actually called pterodactylus. So you're learning physics and you're learning dinosaurs. But actually, Ailish,
Yeah.
was pterodactylus a dinosaur?
No.
It wasn't, was it? Because it flew. And that makes it not a dinosaur, hey? Yeah. Cool. Thanks,
And
Ailish.
Pteranodon can fly, so that means it's not a dinosaur.
That's right, because pterodactylus and pteranodons are examples of pterosaurs, aren't they? Not dinosaurs, they were pterosaurs.
Yeah.
Hey guys.
Yeah.
Yeah, cool. All right, back to forces, hey? Okay, here's an old balance bike. I'll see the force required to lift us up against gravity. I'm using the yellow Newton meter that measures up to 50 newtons of force. And I'm doing this one just because it's a bit heavier, so I won't make the munchkins try and lift it up. So we can see as I start pulling on this, we can see inside the spring balance drops down as more force is required. Stay there, phone. So it's taking about 42 newtons of force to lift that old balance bike up against gravity. 42 newtons of force. Okay, Ailish.
Yeah.
Let's see what force is required to lift your school bag, hey?
Yeah.
Okay, starting with the green one. Hook it on the top. Lift it up. And what happened? Oh, straight to the bottom.
To the bottom.
So the green one isn't strong enough, is it? Right, we'll try another one. Try the brown one. Again. Shh. Right, you got it hooked on? Hook it on. Oh, dear, dear. Okay. Now the force, hold it still. That went straight to the bottom too, didn't it? All right, let's try the next one up. Try the red one.
Okay.
Lift up. Excellent, this one's working because it didn't go straight to the bottom, did it?
Nope.
This is what we want. So, hold it still. So to me that's looking at about 14 newtons of force, isn't it?
Yeah.
Yeah, to lift the bag. Good job, thank you. Okay, so we're back to the car. Now when we lifted the car up against gravity, it took about 4.5 newtons of force to do that, or just a little bit more than 4.5 newtons. So let's see about pulling it along. Alish, can you hook that on please? Now you'll note, we're actually, hang on, don't pull it yet. We're actually using the blue spring balance, which only measures up to 2.5 newtons, so a lot less than what was required before, but let's give it a bit of a pull along. I see that blue one was enough. Okay, stop, bring it back. Oh yeah, don't unhook it.
No.
Hold off, that's fine. Hang on. Put it on there so that I can see the newtons. Alright, that's the grams. You'll note, actually, that's this stuff. Okay, so this spring balance measures up to 2.5 newtons of force. There is actually another scale on the other side. You'll see 250 grams. So you could actually use these spring balances to weigh things as well. Okay, 250 grams is equivalent to 2.5 newtons of force. And that's because on Earth it requires roughly 10 newtons of force per kilogram to lift something up against gravity. It's 9.81 newtons per kilogram, but at year 7 I guess we can just say 10. Right, Alish, let's try this again and we'll make it so that the force is showing on the scale. Right, ready?
Yeah.
So, there it is. So if you pull that along, just gentle. Okay, so firstly it's taken a lot less than 4.5 newtons because this spring balance only measures up to 2.5 newtons. Right, so that's the first thing. A lot less force required to pull it along than to lift it up against gravity. Also, what I'm hoping you'll notice, bring it back, is when we initially start, okay, go. Good. Okay, so with the initial pull, catch it please, thanks, it required a bit more force than once it was already moving. Now that's actually something we'll look at later on when we look at Newton's laws of motion. Okay, the initial force to get something moving is more than the force required to keep it moving. So we'll talk about that a bit later on. This is actually a bit of a cheating one because are we really dragging it along the table, Alish? Not really, because the wheels are rolling, aren't they?
Yeah.
So let's flip the car upside down. Let's not throw the car around, let's just flip it upside down. There we go. Okay, hook it on now. Because now it will just be dragged along, won't it?
Yeah.
Go for it. Okay, stop there. Now that was showing about 0.2 to 0.3 newtons required to pull it along. Okay, we have the same car again. Upside down, so no cheating, no rolling wheels, it's literally being dragged along the ground.
Yeah.
Except before, this was the surface, fairly smooth compared to this surface. This is rough, isn't it?
Yeah.
Yeah, so when you pull it, Alish, let's see if more force is required now, okay? So pull it along. Gently, that's it. Nice. Thank you. Now, hopefully you all realised, or you could see in the video, that the spring balance was pulled down more than it was back up at the table.
Yeah.
Even though we're pulling along the ground, same as we were on the table, but the table was smooth, this ground is rough,
Yeah.
and it required more force to pull it along, didn't it, Ailish?
Yeah.
Yeah. Do you want to know why, Ailish? Do you want to know a good science word?
Yeah.
Friction.
Oh.
You say friction.
Friction.
Friction is a force that opposes motion, and if the surfaces are rougher, then the friction is greater. So we had to overcome the force of friction to get that motion out.
I'll say I actually like science.
Okay, you say that. Right. Ready, guys? Okay, in.
Yeah.
Guys, thanks heaps for helping me. Whoa. Okay, here we go. Take number 57. Thanks heaps for helping me do the science today, guys.
You're welcome. I actually love science.
I know, science is cool, isn't it?
Yeah.
Yeah.
Too.
You love science too? Good job, Ken.
Yeah.
Go, science!
Science! Yeah. Blue.
Right, Alice, did you want to ask something about the safety glasses?
Can I take my safety glasses off?
Yes, you can.